Okay, welcome back to the second time of the lecture of the CS492D diffusion models and their applications. So last time we discussed we basically saw some kind of interesting the outputs of the diffusion models and see what we can generate using some kind of the diffusion models. And from today, we're going to start to discuss some kind of the very basic ideas about the generative models. So for today, we are going to get some kind of the background about the generative models, and then we're going to slowly move to the basic ideas for diffusion models from the next week. And then actually you're going to see that actually there are quite some sort of the math things about the diffusion models and the generative models. So let's see. So what we are going to do with the basically the generative models, the main purpose of the generative model is to basically produce some kind of the new data. So let's think about this kind of case. Let's say we have the tons of some real images that we collected from the internet. So there are actually tens of the billions of images from the internet. Let's say we can collect all those kind of images. So given the tons of kind of the data that we have, some kind of the real photos, for example, can we make a kind of some kind of the framework that can produce another the photos that looks like the realistic photo? So this is basically the problem that we are going to solve, and we are going to see how we can solve this problem over the entire semester. And these sounds like two difficult problems. So how can you really make some kind of the machine that can produce some kind of something like the new realistic photos? So we are going to think about some easier case first. So instead of like having the lots of the photos, let's think about this specific case that we are having a collection of the 2D points in this space. So you are seeing the lots of the 2D points here, right? So given this kind of the collection of the 2D points, if you are basically requested to pick any kind of the point that looks like one of them, how are you going to pick the point? So let's think about the problem that we want to sample a new 2D point that looks like one of the data points that we have. So as like a human being, it's basically a very easy task. We can basically pick one of the point in the space that looks like one of them in the space. But if we want to make some kind of the algorithm or the machine that can do this kind of the 2D point generation, how can you do that? So for that, actually, what we are going to discuss in this course is basically having some sort of the more like statistical perspective. So we are going to see this problem as the case that we are basically having some sort of the underlying the probability distribution of the data. And then those kind of the 2D points or some kind of the images are basically the samples that are basically sampled from the underlying the probability distribution. So then the question is that when you have the lots of the samples that are basically samples from some kind of underlying the probability distribution, how can you basically sample one more point, one more the data point? That becomes basically the problem that we are going to solve. So basically the thing is that if you took the probability and the statistics course, how many of you have taken the probability and the statistics course before? Raise your hand if you have taken. If you just like raise hand here, then I can see like. Oh. Yeah, so this is actually kind of like simple problem in terms of that. If we basically have, if we know the probability the density function of the underlying the distribution, then given this kind of the probability density function, we can just like easily sample a new point. So that becomes like very simple the problem with statistics, right? So let's review some basics in the statistics. So here the question is that if we know the probability density function of the distribution, then how can we sample a new point? This is the question. Do you have any ideas? Like if we know any kind of the probability density function based on that, how can we sample a new point? I guess this is like something that you learned in the statistics course, right? So for those kind of the questions, our TA will basically post the question in our Slack workspace. Then you will be able to basically answer this question in the thread. So would you post your answer in the Slack workspace? Any thoughts? let's say you have some kind of the simple Gaussian distribution in the unit space. Based on that, like how can you make some kind of another sample? So yeah, let's think about this. So basically what we are going to see here is that if the probability density function is known for the data distribution, there is nothing to do. I mean, this is kind of the solved problem. We can just use some kind of the knowledge that we learned from the statistics the course to make some kind of new samples. Let's think about some kind of the easy case first. So let's think about that we are having some kind of a discrete probability distributions. Like for example, let's think about the case that we are rolling a dice. Then there will be 6 the possible values that we're gonna get. 1, 2, 3, 4, 5, 6, right? For each of the value, we're gonna have some kind of corresponding the probability. Then we're gonna basically have some kind of the table of the probability distribution function. And the condition for the probability distribution, the density function is that all the probability should be greater or 0 or the greater than 0. And also the sum should be 1, right? So given this kind of the PDE, how can you basically sample one of the kind of the values? So basically, the simplest idea for that is that we are computing the cumulative distribution the function. So we basically accumulate this kind of probability values over the sequence of the possibility values like this. Then we're going to have some kind of the graph like this, which is starting from the 0 and then reaching to the 1 after like accumulating all the probability, right? So given this kind of the graph, what we can do is that instead of like sampling one of the possibility values, we just like draw a sample in the range from the 0 to 1, basically sampling in the domain of the probability. And based on the value that we are getting from the uniform distribution, we see where this value is basically falling into which of the region, the range of the values of the cumulated the probabilities. So based on this idea, we can easily sample one of the kind of possibility values, right? So this is basically the technique which is called the inverse transform desampling, which is quite intuitive. And this idea can also be easily extended into the continuous case as well, right? So how can you extend this idea for the continuous case? Well, I mean, that can be also very straightforward in terms of that we can also compute the CDF, the cumulative density function, by taking the integral into one of the value in the domain. So we are first getting basically the cumulative density function by taking the integral of the PDF, which will be also the case that we are starting from 0 and reaching to the 1 by accumulating all the probabilities. Then as we have now for the discrete case, what we can do is that once we basically sample from the range from the 0 to 1 using the uniform samples, uniform distribution, based on that, we can take the inverse. So basically, the CDF is basically mapping one of the possibility value that we can take into the cumulative probability, right? So if we can compute the inverse, basically mapping from the cumulative probability into the possibility value here, then based on this kind of the inverse function of the CDF, we can map the random value sample from the uniform distribution from the range to the 0 to 1 to the possibility values x here. So this is basically basic idea that we can do the sampling given the probability distribution, the function. Right? Here, kind of the one sort of the downside is that to sample based on this idea, we should be able to compute the inverse function of the CDF. So this kind of case. So in some kind of special cases that we cannot have some kind of analytic form of the inverse function of the CDF, we cannot directly apply this idea. But for most of the cases, we will be able to use this idea, right? So this is like some basic things in the statistics. And just in case that you haven't seen this before, let me just briefly give you some quiz. So let's think about like this kind of the PDF that we are having this formulation for the PDF from the range from the 0 to 2. Okay. Then from this, if we want to sample a point, then we first need to compute the CDF and also the inverse of the CDF, right? So can you just quickly calculate the inverse of the CDF function for this PDF? You can post this answer in the Slack group space. Yeah, so as you can see, you can easily derive the inverse of the CDF in this case. That will looks like this. Then once we basically compute the inverse of the CDF, then what we can do is that we just draw a sample from the uniform distribution from the 0 to 1, and then we just take this, right? Then that will become one of the samples that we are getting from the given the probability distribution, the density function. So basically, this is kind of like very simple things, like just in case that we cannot derive the inverse of the CDF for the given the PDF, what we can do is that we can also try this idea of the rejection sampling, which is kind of using some sort of the proxy distribution. So while we are basically having the PDF here, instead of like just in case that we cannot compute it, derive the inverse of the CDF for the given the PDF P here, we are taking another the proxy distribution Q here, which is basically the case that we can easily derive some kind of the cumulative the density function. So one of the easiest option for the Q, the upper boundary distribution, is basically the uniform distribution. So we can basically set any kind of the uniform distribution that is basically covering the given the probability density distribution. Then what we can do is that instead of like trying to directly sampling the data point from the given the PDF P, we are drawing a sample from the upper bound distribution Q here. And we check whether we're gonna basically take the point or not by basically taking another sample of the height here. So given this kind of X that we are taking here, for example, from the 0.5 here. Sorry, let me try to write down the slide. Yeah. So let's say this is basically the X that we sampled using the given the proxy distribution, the Q here. And then we are basically taking any kind of the height, the random height with the basically using the uniform distribution. And if this height is basically smaller than the probability with the given the PDF, then we just take this sample. Otherwise, we basically reject this sample. So this is also kind of the simple idea that we can use some kind of another the proxy distribution where we can easily sample the data points from, and then using this information to sample from the given the PDF while basically rejecting some of the samples in some special cases. So these are some kind of the basic idea. Obviously, there are some kind of the bunch of some other special cases that we can even more easily sample kind of the new the points. But basically, it shows that if the PDF of the given the data distribution is basically known, then the generative model is basically nothing but just like sampling some points from the given distribution, right? There's also one more thing is that the many kind of the data, the probability distribution that we are going to see, not only for this lecture, but for the many of the rest of the lecture, will be basically Gaussian distribution. So we are going to play with the normal distribution for many other cases. And for the specifically for the normal distribution, we know how we can easily map any arbitrary the normal distribution into the standard the normal distribution, right? Standard normal distribution is the case that the mean becomes 0 and the covariance, the matrix becomes the identity, right? So even this kind of the mapping from the any arbitrary the normal distribution to the standard the normal distribution and also the other way around, what we can do is that if we want to sample any points from the any arbitrary the normal distribution, we can first make a sample from the standard distribution here, epsilon here, and just like map this to the one of the points, given the normal distribution. So which means that if we just want to make lots of the samples from any arbitrary normal distribution, we just need a sampler from the standard normal distribution. So if we can basically sample any points from the standard normal distribution, we can just like map these points into the sum of the points, the data points of the other target normal distribution, which means that we don't need to have the code for the some kind of all the kind of the Gaussian distribution. We just need the code for the standard, the normal sampler, and then we can just map this into any arbitrary normal distribution. Is this clear? So yeah, basically this is nothing but we are just saying that like it's just like all the matter of like how we can model the data distribution and how we can basically sample from it. In the case that when you can basically model the distribution with some certain form of the probably the density function, right? And even for the cases that like when you generate some kind of the new images, we can see this problem as kind of the same problem. So what we can do is that let's say like we're having the collection of the images, right? Lots of the images. And let's say each of the image is represented as some kind of the RGB image with the resolution, fixed resolution of the 256 by 256, right? Then what we can see is that actually each of the image is represented with the lots of the numbers with the 256 by 256 by 3 because each of the pixels will have the RGB3 values, right? So which means that each of the image is actually a vector, which dimension is 256 by 256 by 3. So this basically means that we can see the collection of the images as actually a set of the points in this very high dimensional space, right? So we can see that each of the image in the collection is basically mapped to one of the points in this high dimensional space. The dimension becomes 256 by 256 by 3. So generating the images from the given the collection actually becomes the problem that we are having a collection of the points in the high dimensional space and basically somehow capturing the data distribution in this space and making a sample from this distribution. Is this clear? So this is basically what we are going to do in this class, in this course. So all the things that we are doing with the generative model is basically seeing the collection of the data as some kind of the collection of some kind of the points, data points in certain dimensional space, and then basically capturing this kind of some data distribution and sampling from it. So this is kind of concept that you should know in terms of like, getting the basic ideas about the generative models. Do you have any questions on this? So basically, what we are going to see is that, let's say this is the case that we are having some kind of the bunch of the samples in this high dimensional space. And given this kind of and each of the point is basically corresponding to one of the some realistic photos, right? Then given this kind of the samples of the points, how can you derive the probability the density function of the underlying distribution? So the thing is that the only information that we are having is just some kind of the samples, but we don't know the underlying distribution, right? We don't have any kind of some analytic form of the probability density function for the underlying distribution. The only information that we have is given the collection of the samples that are basically known as sampled from that specific distribution. So here the question is that if we knew this kind of distribution, it became basically a very easy problem to sample the analytic point. But if we don't know about the given distribution, but we only have the samples, how can we do the sampling based on this information? So for that, basically, what we are going to do for all the generative models, whatever generative models that we have, either the GAN, VAE, diffusion models for everything, what we are basically doing is that since we do not know the exact form of the probability density function for the given the data distribution, we are going to basically start from a kind of simple distribution where we can easily sample the data from. So one of these, some kind of some typical candidate for the simple distribution is basically some standard the normal distribution, because like we know how we can sample from the standard normal distribution, right? And what we are going to do is that we are going to have some kind of the mapping from this kind of some simple distribution that we picked into the data distribution. Then the generation, the process becomes like we are having some kind of the two steps. Like one step is basically sampling from the simple distribution, which is the standard normal distribution, and we know how we can do that, right? And then mapping this sample into the one of the data point in the data distribution. So these will be basically the things that we are going to do for whatever the generative models. Having just the two steps, like one is sampling from this like the simple distribution, and then basically mapping this into the one of the data point in the data distribution. And as kind of the terminology, we are going to call this simple distribution as kind of the latent distribution. So this is not the real data distribution, but we have some kind of proxy distribution. We are going to basically map this to the real data distribution, right? And also one of the sample that is sampled from the latent distribution will be called the latent variable. So the whole process that we are going to do is basically mapping from the latent distribution into the data distribution. So just 1 second. Having some troubles with the Zoom setup. Okay. So this means that we need to have this kind of like mapping from the latent to the data point, right? And here the question is that how we can basically have this kind of mapping. So this is the place where the neural network comes in. For this kind of the mapping from the latent to the data point, we are going to use a neural network. And how we train a neural network for this mapping is all about the things that we are going to discuss for the generative models. Is this clear? Any questions on this? Then what would be basically the idea for this kind of mapping? I'm wondering how many of you have heard about the autoencoder? How many of you have heard about the autoencoder? Yeah. No? There is someone who has never heard about the autoencoder. So we are going to see how this problem is basically related to basically the autoencoder we set up. So the purpose of the autoencoder is basically making a neural network that can basically compress some kind of given input data, right? So the basic idea of the autoencoder is that we are mapping some kind of the given the input data into some kind of the latent variable in terms of that it can be also reconstructed back to the input data, right? So the basic idea is that we basically map the input data into the latent variable and basically recovering this back to the original data again and checking whether the reconstructed data is basically becomes identical with the input data as well. And what we are doing is that we are basically having some much lower dimensional basically data for this kind of like latent here. So in terms of that, we are basically doing some kind of compression, while this kind of the latent in the much lower dimensional space can be also recovered into the original data point. So this is kind of like one of the example that we are utilizing the neural network for mapping to the some given the data, some given collection of the data into some kind of the collection of some kind of latent the vectors, right? So we already have seen this kind of examples, like doing some kind of mapping from the given data into some kind of latent variables. And we are going to use this kind of same idea of like mapping between the two the types of the data to train a generative model. So that's what we are going to do. And here, basically, what we just need is not the encoder, but actually just decoder, right? So if we only have some kind of the good decoder, then what we can do is that we can sample from the latent distribution here and just like map this into some kind of real data. So actually what we just need here is basically just having the good decoder. So you can imagine that like this is the process that we are sampling from the standard normal distribution and mapping this to the one of the real data point using the decoder. But here the question comes from like, how should we train the decoder? Like when you basically map all the latent into the one of the data points, it should be one of the some kind of some realistic, some plausible data point, right? So how can you guarantee that the mapped points from the latent space becomes one of the some plausible data points from the given data distribution? So this is kind of the big problem in the generative models. And all the ideas that we are going to see in this course will be basically like how to design, how to solve this problem. Clear? Any questions on this? So how we solve this problem? For that, basically, we are having we are going to see the two basic ideas for that. One is like GAN, and the other one is the VAE. And while we discuss these two basically main ideas, we are also going to see next time on how the diffusion model has been derived based on some kind of the advances in the GAN and the VAE. So before we get into the diffusion models, we are going to briefly discuss the basic ideas like this GAN and the VAE. And next time we are also going to see how these ideas are related to the kind of the birth of the diffusion models. Okay, sorry, has some issues with my iPad. 1 second. Okay, let's first move on to the GAN. So GAN is kind of like was the most basically the famous idea for the generative models. And before the diffusion models, basically everyone was basically using the GAN, right? So what we are going to do with the so just 1 second. Give me just like 1 second because like my iPad has just died. Okay. Okay. Oh. Okay, is the sound okay? Can you even see my slide? Okay, so let me continue. So we are going to start to see the idea of the GAN. So before we get into some the basic idea of the GAN, let's first see this kind of some off-topic things. So we know that actually neural net is quite good at like many kind of the tasks. Like one of the tasks that neural net is really good at is the classification, right? So even like more than 10 years ago, like we could basically make some really good classifier based on the neural network that can classify all those kind of images into the like the buses and into the I don't know dogs and the pyramid, kind of like many kind of things. So after we see some really good quality of the classifier, the question is like, how vulnerable is the neural network? How basically stable the kind of the performance of this kind of the classifier? So the experiment here is that, let's say we are having some kind of like, there was basically a classifier that could basically successfully classify all those kind of like 6 images on the leftmost side. So those are all the images that are correctly classified using a neural network. And can you tell the difference between the leftmost image with the rightmost image for each of the left and the right hand side? So we are basically having very similar images on the left hand side and the right hand side, right? I personally cannot tell any difference between these two. And the second column here is basically visualizing the difference between the left image and the right image multiplied by the 10%, 10 times, showing some kind of some difference of the pixel colors for each of the cases. And you can see that the difference between these two are very small, very tiny, basically making very small perturbations into the images on the left-hand side. But what happened is that if we make some this kind of like adding very small noise, very tiny noise on the leftmost images, what we can get is that we are seeing the results that the previous classifier classifies all these images into the ostrich. Do you know like what the ostrich is? Ostrich is this. So it's basically very surprising that we can easily like confuse the classifier in terms of adding some kind of some perturbation into the images, and the classifier turns to basically classify all these kind of like images into the wrong class, which becomes like ostrich in this case. So this basically shows like how vulnerable is the pre-trained classifier is. So there can be basically some ways that we can easily attack this kind of some pre-trained neural network, right? So we can really even think about like making some kind of the neural network that plays the role of the offense. So let's think about like just like having some sort of the adversarial attack, which basically means that we are basically making another neural network that basically tries to predict some kind of a small amount of the noise. We're basically making just like another image that is basically confused by the pre-trained classifier. So let's think about some kind of like making another neural network that tries to find some kind of the failure cases of the pre-trained the classifier. Then now we can also use this kind of the another neural network to improve the given the classifier. So we can also try to fine-tune the given the classifier in terms of that it can now make some kind of the correct the prediction for some kind of images that were produced by the other network, right? And then what can you do? We can also improve the other network as well. We can also improve the adversarial attack network in terms of that it can produce some more like find some kind of the failure cases that is still basically confusing the given the classifier. So we can basically make them to compete each other. Like one is basically attacking the other neural network, and the other network is basically defending from the other network, right? So when you basically make this kind of the competition between these two networks, what will happen? So this is the basic question. So in the generation this setup, what we can think about is that we can think about like having the decoder in the previous slide, which is now the generator. So the decoder or the generator is basically mapping some of the latent variable into one of the vector in a way that we hope that this becomes some kind of the realistic image. But this is still kind of the fake image, right? Synthetic image synthesized by our kind of decoder. This is not the real images, right? But we hope that the synthesized images from the decoder will basically confuse the other classifier, which is classifying the real and the fake images. So for the other classifier of the network, which is the discriminator, the role of this network is basically taking either the real images that are basically given from the data set or some kind of the synthesized images that are basically created from the generator, and basically classifying whether this is the real or the fake. So now the discriminator plays the role as the classifying the real and the fake images. And then we are basically competing this classifier with the generator, which will try to make some kind of the more realistic images. So from the competition, we hope that the generator will be able to make some really good fake images that really looks like the real images. So that's the basic idea of the generative adversarial network that was introduced like more than 10 years ago. So like we're basically having some kind of the two neural network, like one is the generator, which was the decoder in the previous slide, which is taking the latent sample from the unique Gaussian distribution and mapping this into the one of the synthetic images. And we just train this network in a way that this synthetic image becomes like very hard to be differentiated from the real images. And then the discriminator is now taking either these real or the synthesized images and classifying these into the real or the fake. And we're gonna make these to compete each other. So let's quickly see how we can exactly make them to be to compete each other. So this is kind of the loss function that is basically used to train both of the networks. And we are having the two networks here, right? One is the generator and the other one is the discriminator here, right? So let's basically see each of the term of this loss function one by one. So basically, first we are taking the sample of the real image x here. So x here is one of the real image that are basically sampled from the given the data set, the training data set. And z here is basically one of the sample that we are taking from the unique Gaussian distribution, from our latent distribution, right? So we are having both basically x and the z. So over the entire slice, we are going to use the x as kind of the variable representing one of the some real images, and z as kind of the variable representing one of the latent the variables. And given these kind of samples, what we are having is that d is basically the generator, right? Which will basically map the sampled the latent variable into one of the some synthesized image, right? This is the fake image that we hope that it looks really like the real images, right? So GZ is basically the fake image here, right? And given this, we are also having the discriminator, which is basically measuring the probability of the real images, or like probability of like the whether like the how likely the input image is a real image, right? So when we take the dx, this is the probability for the given the sample of the real image, and here the dgx is basically the probability of the like realism of the given the synthesized the fake image, right? Is this clear? And then if we see the loss function, then we can say that actually we are combining minimization and the maximization. So this is kind of very, of course, some sort of the optimization function in terms of that we are maximizing the overall the terms with respect to the parameters of the discriminator. So from the discriminator the perspective, what we are going to do is that we want to increase the probability for the given the real image x here, right? That's what we need to do. And we also need to minimize, decrease the probability for the given the synthesized image ZZ here, right? So we are training all the networks in a way that we are maximizing everything with respect to the parameters of the discriminator in terms of like increasing the probability for the real images and decreasing the probabilities for the fake images, right? But from the perspective of the generator, we need to do the opposite. We need to minimize the whole things, which will be the case that we are actually increasing the probability for the given the synthesized images. So this is kind of the crazy the optimization, the objective function for our the optimization. For the same basically the formulation, for the discriminative perspective, we are going to maximize this, and from the generative perspective, we are going to minimize this, right? But you can clearly see this kind of the competition relationship between the discriminator and the generator. Like one is trying to maximize some quantity and the other one is trying to minimize the quantity, right? But over the training of this kind of the process, so like training both the discriminator and the generator, hopefully we will be able to see that actually the generator is basically improving the quality of the fake images in terms of that it becomes very realistic. It can be very difficult to be differentiated from the real images. But this is the case that like when everything goes really well. But as you can see, like solving this kind of optimization the problem is really difficult problem, which means that when you train the network with the gradient descent, with the backpropagation, actually there will be quite many failure cases. So if you have any experience in training the GAN, then you would know that training GAN is really challenging the problem. So we will see that there are quite many failure cases. Like very typical the failure cases of the GAN is that it's not like competing each other, but like discriminator is dominating everything. So the very typical the failure cases of the GAN training is that the discriminator becomes very strong at the very beginning, which means the discriminator can very easily classify the real and the fake images. For those kind of cases, when the discriminator becomes like very dominating the training the process, then the generator cannot be improved with the training. So that becomes the typical the cases that the neural net training is not converging to the ideal case that we want to see. So even in the cases that when it basically converges well and basically improving the quality of the generator, the other some kind of typical failure cases of the GAN is that we are seeing these kind of results. So these are basically visualizing some data distribution, the red here. So red points, dots here are basically visualizing the ground truth, the real data distribution. And blue is basically the output of some kind of some generating the samples using the GAN and the framework. So the blue basically shows some kind of the reconstructed the data distribution for the given the collection of the data. And you can see that there are some kind of these are some failure cases that the reconstructed distribution is not capturing the overall the distribution, but just like collapsing to each of the mode, each of the some kind of the subset, some the cluster of the. So this is also very the typical the failure cases that the GAN cannot capture the entire distribution of the given the collection of the data, but basically just like focusing on like a small subset and want some kind of the cluster of the points, and just collapsing to the specific mode. So this is kind of the problem called the mode collapse. And there have been lots of the efforts, like tons of the efforts to handle this kind of instability in the training and also the mode collapse issues. So there have been lots of some kind of the previous work that tried to basically solve these kind of the issues, the problems. So you can also check out this kind of the previous works. And before we see the diffusion models, like this kind of the GAN idea was kind of the dominating the method in terms of training the generative models. So as I also mentioned in the previous lecture, even like 5 years ago, even way before the diffusion of the models, the quality of the generative models that we could see was actually really very good. These are all some kind of the synthesized images using the GAN. And you can see that these output were already very realistic. But the reason like why we could see some kind of the rise of the diffusion model was that was basically provides some kind of even better quality, better the performance than the GAN the framework, and also it has some kind of the lots of the advantages in terms of like making the training to be much easier and converting to much faster and easier. So there are some much kind of disadvantages than the GAN. So we are going to discuss some kind of these kind of advantages of the diffusion models from the next week. Any questions about GAN? No questions. If you have any questions, feel free to post the questions either in the Zoom chat or the Slack workspace. Actually, it's better for me to post the questions in the Slack. So let's see. So this was kind of like very basic idea for the GAN, which is like quite intuitive and straightforward. And then now we are moving on to the VAE. And I'd like to tell you that now we're gonna see some kind of the math here. So the basic idea of the VAE is that how we are going to also make some kind of degenerate models without solving the minimax problem. So all the problems of the GAN comes from the fact that we are basically having the optimization the problem that's basically solving a minimax problem, like making the generator and the discriminator to compete each other by basically minimizing or maximizing the same objective function in different times. And this basically makes the optimization becomes like very unstable. So without solving the minimax problem, how we are going to make a kind of generative model? So this is the part where basically we start to discuss the VAE. And for that, we are going to basically do this kind of thing. So we are going to basically represent the mapping from the latent distribution to the data distribution as some kind of like sampling from the conditional distribution. So we're gonna start to see some kind of the ideas like introducing some conditional distribution. So this was basically the case that we are having some kind of the unknown data distribution. We have some kind of underlying but unknown distribution. We only have some kind of samples from there, right? And what we want to do was basically we are having some kind of the given and fixed sample the latent distribution and sampling from here and then mapping this to the one of the data points, right? And now we are going to basically represent this mapping as kind of also another sampling from the conditional distribution. And there can be lots of the way that we can basically also model this kind of the conditional distribution. But to simplify everything, we are also going to model this kind of conditional distribution as another the Gaussian distribution, which is basically taking the output of the decoder as the mean and having some kind of the fixed variance here. So the changes that we are making here is that now we are also seeing this kind of the mapping from the latent to the data point as basically sampling process from the conditional distribution. Make sense? So based on that, we're gonna get into some more details. But before we that, let me also briefly review some of the basic ideas about the statistics. Are you familiar with all these kind of terms here? Is everyone familiar with all the terminologies here? No? Yes? Raise your hand. If you don't know any of those things, would you please raise your hand so that I can see? Is everyone okay to just like go over those things? So just in case that you are not familiar with any of those kind of things, let's very briefly go over with these kind of the basic concepts, okay? So marginal distribution. Marginal distribution is basically nothing, but basically when you have some kind of the joint probability distribution for the multiple the random variables.
the marginalization is basically the process that we are basically getting the probability distribution only for the subset of the random variables. So for example, like in this case, like when you have the both the x and the z as the random variables, what we can do in terms of like marginalizing for the x is that we just like take the integral over the z. In terms of that, we only have some kind of the marginal distribution for the given the x here. Right? So this will be called the marginalization. So let's do some kind of a very easy exercise. So let's say this basically shows some kind of the joint the probability for the given the x and the y here. And if we want to get some kind of the marginal, some kind of probability for the given x, what's the kind of the probability that x becomes the 1? Yeah. Should be 0.36, right? Just like summing up all these values, right? Then next, I mean, everyone should know basically expected value, right? Expected value is basically nothing but just like taking the mean of all the possible values while weighting them with the probability, right? So this is like literally the value that we expect to see, right? So weighted the kind of the average of some kind of the possible values, weighted by some kind of the probabilities for the potential the outcomes, right? And let's also try to calculate the expected value. So given the kind of the marginal distribution over the x, can you also compute the expected value of the x? So we can first compute px1, px2, and px3, right? It's becomes the sum of each of the row, right? And once we have this, like we multiply this by the possibility values, right? If we take the sum of this, then this output becomes like 1.96, right? So yeah, easy. Base rules, I guess most of you would know the base rule, which is basically showing some kind of the relationship between the marginal distribution and the conditional distribution, right? So basically from we know this kind of fact, like basically connecting this some kind of the joint the distribution with the conditional and the marginal distributions, right? So given this kind of the some relationship between the conditional and the marginal and the joint distribution, from this we can derive this kind of some kind of the relationship, across them, right? So given the prior and the likelihood, which is basically the conditional distribution from the z to x, we can basically compute. We can see the relationship with the marginal distribution here and the posterior distribution here, right? So given basically the kind of some distribution, like it can be like latent distribution in our case, right? Basically, if we have basically likelihood, which is basically mapping from the z to x, then based on that, we can now compute the joint, for example, here, given the given the latent distribution and the conditional distribution that we are learning with the decoder. Based on that, we can see that we are but now having some kind of a joint distribution between the x and the z here, right? We can easily calculate all those kind of things. Let's do one more some kind of the simple exercise. So given this kind of the joint, probably the table, can you compute the conditional probability of the y becomes 2 given that x is 1?
So by the way, if you are not familiar with those kind of basic things, and if you don't know how to solve those kind of the some simple the questions, then the rest of the topics that we are going to discuss in the rest of the course can be challenging. So you can basically tell like whether this is kind of the right course for you in terms of like getting some kind of basic understanding of those things. And obviously, this is kind of like very easy in terms of that. This multiplied by the px to be 1 should be the joint distribution, right? y2 and x1, right? We computed this before, and this is from y is 2 and the x is 1 here, right? And from these two numbers, like we can now calculate this to be like 1/12. Right? Simple things, right? And then the next is the callback liability divergence. So we are not get into the any details of the callback liability divergence because like only for this topic we can actually talk about this like for 1 hour, right? But the basic idea for the callback liability divergence is to basically have some kind of the measure or like the distance between the two distribution. But it's not actually a distance. So basically this is basically measuring how close like the given the probability distribution P is to the given the reference probability distribution Q here. So when you have the two probability distribution, this like the divergence is giving some kind of the measure of like the closeness from the one to the other, from the P to the Q. So here's the one quick question is that if we measure this like the KA divergence for the same probability distribution, so when given the probability distribution P is the same with the reference the probability distribution Q here, if these two are the same, then what should be kind of the number we should get? This is easy, right? And this should be 0, right? And we are not gonna get into some details, but actually you can prove that the minimum number of the KA divergence should be 0. So the KA divergence cannot be negative value. All the KL divergence should be non-negative value, which means that this KL divergence becomes the minimum the value when these two given the distributions are basically identical to each other. So this basically shows that as this KL divergence is close to 0, we are basically seeing that these two distributions are basically close to each other. And one more the question is that is this like the KL the divergence is the same with the taking the distribution the other way around? So when we measure the KL divergence from the P to Q and the KL divergence from the Q to P, is this the same or not? Can you guess? Yeah, so the answer is that these two may not be the same, right? So this is like why this cannot be called as kind of the distance. So this is basically some kind of distance is kind of the symmetric measure. So whether you basically swap the P and Q or not, the output should be the same. But for this like KL divergence, like if you swap the P and the Q here, then the quantity becomes like different. The only case that like when these two become the same is like when the P and the Q are the identical, when they are basically 0. Otherwise, these two quantities may not be the same. So this is why like this divergence is not the distance kind of the measure, but some kind of the measure of like measuring asymmetric the measure of measuring the closeness from the one to the other. And we can actually really calculate the exact value of the KL divergence for some kind of the well-known some kind of the analytic form of probably the density functions. So like one kind of like example might be is like when you have some kind of the arbitrary some normal distribution or with some kind of the random mean and the covariance here with some kind of isometric the variance. When you also have some of the standard the normal distribution here, if we measure the KL divergence from the P to Q, what should be quantitative like this? So you can check out this. We are not gonna into the details because of the lack of time, but I strongly recommend you to basically try to basically solve this problem yourself. We can easily find this answer in the internet. We can also ask ChatGPT to get this, but I recommend you to basically try to solve this yourself. Okay. One more thing is basically the Jensen's inequality. So to talk about the Jensen's inequality, we're gonna first see the definition of the convex function. So everyone would know about the meaning of the convex, right? But what's the meaning of the convex function? So convex function is the case that we are having some kind of the convex shape of the function, the downward of the function. So when you have some kind of the verge of the function like this to the downward, so what we can see is that this is basically comparing these two cases. Like the first one is basically taking two endpoints here, taking the no, you don't need to submit the homework. I mean, this is just, yeah, there's nothing to submit. You can just try yourself. So let's continue. So here, basically, we're having the two endpoints, x1 and the x2. So if the function is convex, then what we are going to see is that when you first interpolate these two endpoints in the domain and evaluate the function, then you're going to get this, right? And then when you first evaluate the functions for those two endpoints and interpolate these two, it will be the case that always is kind of second case, like evaluating function first and then interpolating will be the same or greater than the case that we are interpolating first and evaluating the function, right? This is basically the definition of the convex function. So when the function is basically having some kind of the convex shape to the downward like this, for all the cases over the entire domain, we're gonna see the results that evaluating functions first and then interpolating will be same or greater than the interpolating and then evaluating the functions, right? So we're gonna go into the Jensen's inequality based on this. And this is for the 1D case. And the same idea can be basically applied to the any kind of the multi-dimensional function. So even for the any kind of like multi-dimensional functions, if we basically have some kind of the multiple points in the domain, and basically if you take any of the kind of the point in this convex of some kind of the endpoints in the domain, basically taking some kind of the affine the combination of any kind of the given set of the kind of the data points. If you compare these two cases, like first evaluating and taking some kind of the interpolation, and then interpolating first and taking the evaluating the function. If the function is convex, that means that these should be always same or greater than the previous case. So this is the definition of the convex function. So this holds when we take some kind of the affine, it should not be, it should be I, right? Yeah, and for any kind of Ti, right? And also the sum of the Ti should be 1. So this is the case that we are taking some kind of affine, some kind of the combination of the given points, right? So for all those kind of cases, if basically this holds, this means that the function is basically convex. And the other way is also the same, right? And based on this, what we can also see is that, actually we can see that taking the expected value is the same as kind of taking the affine combination. Because we know that now the weights becomes the probability, right? Probability is basically the non-negative value. And we know that the sum of the probability also becomes the 1. So actually, taking the expected value is the case that we are taking some kind of the affine combination. So for the cases like when we are taking some kind of the expected value, this property for the convex function will hold. Basically, taking the evaluating the function first and taking the expected value should be equal or greater than the case that we are taking the expected value and evaluating the function, right? So this is called the Jensen's inequality. This is basically nothing but just like based on the definition of the convex function. Is this clear? And what happens for the concave function? You can now guess the meaning of the concave function, right? So convex was the case that we are having some kind of a convex shape like this, and basically any interpolation of the function becomes like greater than like this case. Concave is the case that we are having the opposite. Now we are having the convex shape like this. So if you basically evaluate the function and take the interpolate
or like these two, it becomes equal or it's basically smaller than the case that you're first interpolating and evaluating the functions, right? So for the concave decrease, like this inequality will become the opposite. Make sense? What's kind of the concave function that you know? So the concave function that we are going to see in the later of these slides will be basically the log function, right? The log function looks like basically this. So which is basically one of the concave function, right? It is clear? So yeah, these are some kind of the basic things to understand the rest parts of the VAE. So if you haven't heard about some of those kind of things, please check out those details, and you can also come back to this kind of previous slides. Okay. So let's get back to the VAE. So what we are going to do here is that we are having some kind of some prior distribution, which is the latent distribution. Let's say we just like fix this as kind of standard normal distribution. It doesn't need to be standard normal distribution. You can also come up with some kind of the other cases, but let's just simplify all the things. So let's say the latent distribution is simply a standard normal distribution. And then we are also modeling the kind of the likelihood, the mapping from the z to the x as another the Gaussian distribution, which mean is predicted by our decoder, right? So from the statistical perspective, from these two, what we want to do is that we basically want to maximize the marginal probability. So given some kind of the samples of the real images, what we want to do is that we want to model these things, especially like modeling this, right? Because like this is already fixed. So we want to model this in terms of that we maximize the probability, the marginal probability for the given the data point dx here. So here the question is that how can you do that? How can you model this kind of likelihood distribution in a way to maximize px? So what we can do is that, sorry, let me check the here, you mean in the previous one. So the question here is that what's the I here? Is the identity matrix is that one in the high dimensional space, multi-dimensional space. Okay. So basically, what we want to do is that to compute this kind of the marginal probability, we just need to take the integral of this. And we can also approximate this integral by just taking lots of the samples of the x and the z here, right? That's kind of very typical the technique called the Monte Carlo sampling, the method, which is basically nothing but since we cannot directly compute the integral, we are just taking lots of the samples of the x and z and taking the sum of them. But if we want to really get some very precise px here, then we will need tons of the samples of the x and z in the multidimensional space. This will be basically very time consuming. So instead of like taking the integral, the other way that we can basically compute the px is that we are using the base rule here. So using the base rule, actually we can now compute this kind of the marginal distribution based on the given the prior distribution, the likelihood, and also the posterior distribution here. This is nothing but just like using the base rule, right? But here the thing is that we know this prior distribution, right? This is given as the unique Gaussian distribution. And this is also what we are going to learn using our decoder, right? And if these are given, actually there should be some kind of a conditional distribution of like the other way around from the x to g, right? But there should be some kind of the underlying the conditional distribution. The thing is that we don't know what this is. We just like basically we fixed this and we learned this. And if these two are given, then this posterior distribution should be somehow given in some form, but we cannot directly calculate this. So this is the problem. If this posterior distribution was basically known, then we could directly compute this marginal distribution. The problem is that now we don't know this. So without like knowing this, like how we can do some kind of the good approximation, have the good approximation of this px. This is the whole idea of the VAE. And we're going to also get back to this idea for the diffusion models as well. So this is kind of the most important part. And this will basically get more like complicated. So let's see. So here the idea is that like we don't know this posterior distribution is like PZ conditioned by the X, right? But while we don't know, we are going to compute the PX here, actually exactly the log of this kind of the probability with some kind of the lower bound. So basically the things in this kind of the box here, the red part, is something that is known as kind of that it becomes the lower bound of the log of the marginal the probability here. It is guaranteed. So which means that what we are going to do is that instead of like, so since we cannot directly compute this probability, what we are going to do is that we are not computing this, but computing this. And we try to maximize this as much as possible. So if we maximize the lower bound, then that will be the result that we are also maximizing the probability, right? So this is what we are going to do because we cannot directly compute the PX here. And so this is basically the formulation which is called the evidence lower bound, which is basically meaning that like it's the lower bound, which is also guaranteed to be lower bound, right? And for that, what we are doing is that you can see that actually this is like very similar form with this kind of the Bayesian, right? The some kind of the formulation from the Bayes rules, right? But the only difference is that now we are not taking the exact given the posterior the distribution, but we are having some kind of some different distribution, right? So this is kind of some proxy distribution again. So since we do not have some kind of the information about the exact posterior distribution, we are going to have some kind of the proxy. You can think that this is kind of a arbitrary distribution, which may not be exactly the same with the ground truth, the posterior distribution, but hopefully it's actually better. This is close to the given the posterior distribution, but yeah, it can be any arbitrary distribution, conditional distribution given the X to the Z. So for example, like one way that we can basically make this kind of the proxy distribution is that we are basically having some kind of the function like this. So making some normal distribution is with the Z, but basically having some kind of the function that is basically mapping the given X into some kind of the mean value here. And also basically mapping the input X into some kind of the variance here. For whatever functions here you have. You basically map given the X into the mean of the normal distribution and also the variance of the normal distribution. And that becomes the proxy distribution. It doesn't matter whatever kind of some sort of the mean and the variance here. So if you have this kind of the proxy distribution, it doesn't even need to be normal. Well, we're gonna simplify everything into making everything is kind of normal distribution, right? It doesn't need to be normal distribution, but if you have any distribution here, then this basically the relationship like making the lower bounds will hold. But also it's the matter of like how we find some kind of the good proxy distribution here. In terms of that, we can also maximize the whole the lower bound here. In terms of that, we can also maximize this PX here. It is clear. So here the main idea is that since we cannot directly compute the PX, we're gonna compute the lower bound here using some kind of the proxy distribution here. And what we are going to do is that we want to somehow find some kind of the good proxy distribution DQ here in terms of like maximizing this kind of the lower bound, which will result in the case that we are maximizing the PX here. So what is the log P is greater than the expected value? So that's basically what we are going to see in the next of this slide. So, but you can see like there are some kind of the analogy between this form, the real form of the PX here, basically having this. So instead of like having this like P, the posterior distribution here, we are just like replacing this into some kind of the proxy distribution and taking the expected value. It is clear? And why this is basically becomes the lower bound. This is basically because of the Jensen's inequality. So let's just quickly see this like one by one. So from the the marginalization, so this is basically nothing but basically taking the marginalization, right? So we compute the PX as kind of the integral over the joint the probability over the Z, right? So this is basically nothing but marginalization. So this is just like the one. We're just like multiplying one. with the having this term both for the denominator and the denominator, right? And what we can see is that now we can see this whole the integral as kind of the expected value, while basically taking this as kind of the probability, right? So you can see that now we are taking these parts as kind of the probability, and the rest of the part as kind of the value that we are taking the expected value, right? Then now we are having this expected value, and we are taking the log of the expected value. And from the Jensen's inequality, we can see that actually this becomes equal or greater than this case, taking the log first and then taking the expected value. So this comes from the Jensen's inequality. Okay? So by combining the facts that we just discussed in the previous slides, we can see that this really becomes some kind of the lower bound of the some log of the probability we want to get. Okay. Any questions on this? So we are using the fact that the log is the concave function. So here's one quick question that we can see is that then when these two becomes identical, right? So this is basically the lower bound. Then when this becomes the same with given the probability the distribution, the probability values here. So this difference between these two is called the Jensen gap. Then I also recommend you don't need to submit this, but I strongly recommend you to just work on this at home. Just like see when these two become zero and what's basically exact quantity of the difference between these two. Clear? So as kind of the last slide, so let's quickly see this. So now basically what we basically want to do is basically working on this kind of ELBO, basically the lower bound, and we're gonna try to see basically how we can maximize this, right? So to maximize this, what we are first going to do is that let's first decompose this into the two terms here. But this is nothing, but you can just like take this slide for a while, and you can see that no, we are decomposing this joint probability into this form. And here we are taking this into this out. And then I'm also flipping the denominator and denominator here, these two, and flipping these two while taking the minus here, right? And now you can see that actually the second expected value becomes the form of the KAL divergence that we have discussed in the previous slide. So yeah, however I explain this, I think you will need to basically check out this slide after this lecture and see what's the meaning of like this. And what we can see is that basically we are having this term. This is the term we're gonna call as the reconstruction term. And you can see that we are maximizing this reconstruction term, right? While we maximize this, what we also need to do is that we also need to minimize this, right? Because of the minus here, right? So this is basically the KL divergence. So minimizing this basically means that we want to make this kind of the proxy distribution to get closer to the latent distribution, which was the unique Gaussian distribution, right? So what we are going to do is that we are going to basically maximize this kind of the reconstruction term. We're gonna see basically how we can maximize this. While we maximize this, we're gonna make the proxy distribution to get closer to our kind of the latent distribution, which was basically the unique Gaussian distribution. So we are basically working on this in terms of maximizing the ELBO function. So since we are running out of time, so we're gonna get into how exactly we can maximize this ELBO function in the VAE formulation. And then we're gonna also see how this is like related to the diffusion model that we are going to see in the next week. So that's what we are going to do in the next Monday. Any questions on this? So as you have seen, like there are quite some kind of the formulations in the slides. And I think that however I explain all the things, you will need to take a look like those slides yourself and try to write down the formulation and see how these are basically derived. And I like to tell you that from the next lecture and the other lectures, actually we're gonna see some more formulations. All the ideas in the diffusion models are all based on this kind of some statistical deforms. So the plan is that we're gonna see this kind of some more like
some foundational things about the diffusion models for the next few weeks. And then we're gonna go over into some more application related kind of things, like how we design the neural network and how we basically implement all the things. And then we're gonna get back to some more like the theoretic ideas about like improving the diffusion models after the few weeks. So that's the plan. And if you have any questions, please feel free to post your questions in our Slack workspace. And me and our TAs will basically work on all your questions. So if you don't have any questions, then I will see you next Monday. Okay, thank you.